Okay, good morning. So today we're going to, as I mentioned last week, we've started the part of the course where we're doing more things having to do with design, okay, than purely analysis. Today we're actually going to do analysis, but it's a type of analysis that leads to really interesting design issues. And we're going to follow it up on Wednesday with an application of the methods we're going to learn today to a really interesting and practical problem. So we're talking today about amortized analysis. And I want to motivate this topic by asking the question, how large should a hash table be? So how large should a hash table be? Anybody have any suggestions? Got to make a hash table. How big should I make it? Let's say it's a simple hash table, resolving collisions with chaining. How big should it be? Twice as big as you need. Okay, how big would that be? So twice the number of elements, for example. Okay? As I increase the size of the hash table, what happens to the search time? What happens to search time as I increase the size of the hash table? Yeah, but what does it in general do? It decreases, right? Okay? The bigger I make it, in fact, if I make it sufficiently large, then I essentially get a direct access table and everything's worst case order one time.
I would like to try to defend Kant on this point, and then I want to see whether you think that my defense is plausible. And I would want to defend him within the spirit of his own account of morality. Imagine that someone comes to your door. You were asked the question by this murderer. You're hiding your friend. Is there a way that you could avoid telling a lie without selling out your friend? Does anyone have an idea of how you might be able to do that? Yes, stand up.
I was just going to say, if I were to let my friend in my house to hide in the first place, I'd probably make a plan with them. So I'd be like, hey, I'll tell the murderer you're here, but escape. And that's one of the options mentioned. So.
But I'm not sure that's a Kantian option. You're still lying, though.
No, because he's in the house, but he won't be.
Oh, I see. All right, good enough. One more try.
If you just say you don't know where he is because he might not be locked in the closet, he might have left the closet, you have no clue where he could be.
So you would say, I don't know, which wouldn't actually be a lie because you weren't at that very moment looking in the closet.
Exactly.
So it would be, strictly speaking, true.
Yes.
And yet possibly deceiving. Misleading.
But still true.
What's your name?
John.
John. All right, John has, now John may be onto something. John, you're really offering us the option of a clever evasion that is, strictly speaking, true. This raises the question whether there is a moral difference between an outright lie and a misleading truth.
The resulting Bragg scattering pattern depends entirely on the periodic nature of your lattice. So in our own experiment, the way we do it is we have a green laser, helpfully colored green on the slide, and it shines up through the microscope objective and comes in kind of at an angle with respect to our lattice, hits the lattice, and then scatters off and comes out of the objective, and then we project it onto actually a piece of lined notebook paper. So we can talk about different modes of scattering. So up there, there's one not dotted line that's labeled the 0, mode, and that's the unscattered light. That's the green light that just goes through the lattice, doesn't hit anything, and comes out.
Nothing quite like it was ever done before, wrote C.S. Lewis shortly after publication of the first installment of his friend J.R.R. Tolkien's epic, Lord of the Rings. Lewis spoke with some authority, not only because he was a professor of literature, but because he had the rare privilege to watch the creation of the Lord of the Rings firsthand. Indeed, he had been the story's chief booster during the 12 years that it took Tolkien to write it from 1937 to 1949.
Today, we turn to a discussion of theory and models. You recall in an earlier lecture that I raised the following issue. Research in communication takes as a hallmark the understanding of theory and the application of that theory to certain kinds of models. In these models, we try to find evidence. We seek prediction, how the model might be useful in other cases, explanation, how we might be able to articulate the information, and its accuracy, the truth, the validity, and reliability of the information we've gathered. In his book Discourse, A Critique and Synthesis of Major Theories, he takes as his basis the field of composition theory, and he applies these general categories of theory to the field of composition, and he says, yes, composition theory should establish universal typology by classifying instances of discourse, and in a later lecture we'll see how the great theorist James Cavady did that in his theory of discourse. Lays it out quite well by Fishbein and Asian. In the top we have the diagram, and theorists again love to draw diagrams. We'll pursue that in later lectures as well, the visual representation of ideas. The person's belief that the behavior leads to certain outcomes and his evaluation of that outcomes. The particular belief that an individual has that we might call, early on in this a kind of attitudinal belief.
So our delta H of this reaction is equal to minus 1170 kilojoules for this reaction. And all we did is we took the heat of formation of the products, multiplied times the number of moles, and subtracted out the heat of formation of the actual reactants. So there you go.
Storyboard up when you're dragging it out. And I'm going to show you how to create multiple storyboards today in the demo. The split view is generally a base element only, like it fills the whole screen. You wouldn't have a split view inside of a navigation controller or inside of a popover or something like that. Generally, the split view is one of them, and it's for your whole app, generally. It might even be restricted to be that. I'm not 100% sure of that.
We're in the Museum of the Cathedral of Siena, and we're looking at probably the single most famous work of art from Siena, certainly one of the most important works of art from the 14th century. This is Duccio's Maestà.
The title means the Virgin Mary in Majesty.
And we see her very large in the center of the main panel. She is by far the largest figure anywhere in this painting.
This is a polyptych. It's made out of many, many panels, not all of which are here. here in the museum, unfortunately. The Maesa is painted on both the front and the back. So Mary's on the front, and stories of Mary's life are on the front, but the story of Christ is on the back.
So in a sense, this is a freestanding painting. It is this large sculptural object that has all this imagery all over it.
And the figures, the saints and prophets and angels, are almost life-size.
It's true. There are 3 rows of them, and they're lined up almost as if it were for a class picture. There are 4 local saints in front, and then angels and saints in the second row, and I think a unbroken row of angels in the back. Now, in the previous century, Siena had won a significant battle against its arch rival, Florence. Now, both Siena and Florence were wealthy city-states, that is, they were independent nations, and they were often at war with each other. Siena believed that they won because of the grace of Mary.
Hi folks, I'm David. You might remember me from lectures. I'm your friendly neighbourhood physics lecturer. This is a short instructional movie trying to illustrate some of the things that we're trying to talk about in lectures using maths. So it's a little bit like an amateur magic show, but the precision of what we're trying to do is helped by the fact that we have some very carefully cut out things out of cardboard. Thank you, Rolf Harris. So you can see that they've got almost the same dimensions, same diameter, same height, but this one is made out of denser material. This is made from aluminium. You can tell that because it's that kind of shiny, dull, aluminium looking like thing, and this is made out of plastic, it's black. So they've both got the same mass. We're trying to keep things as constant as possible, so we can find out what the effect of the distribution of mass is. Is the fact that the mass is all on the outside important, or is it just the mass that matters? We know if we're dropping them that they'll both hit the ground at the same time because they've got the same mass, and more importantly, they've got the same shape. The air resistance is going to be very, very similar. We also know, on top of that, that even if the masses aren't the same, the acceleration under gravity is going to be the same, which is a really important point to get across. So in this case, we might confidently expect that they would both roll down a plane, accelerating in the same way, and get to the plane at the same time with the same speed. So the trick now is to try and predict that. We use the words weight and mass interchangeably. I do it the same as everyone else. I talk about something weighing 100 kilograms when I'm lying to my dietitian. So my dietitian gets me to weigh my food out on scales. Here we have some scales. We can see that one of them is 109 grams. The other one is 91 grams. So this black thing has a higher mass. It also has a higher weight under the same gravitational field, which is a distinction that, although in everyday language we don't very often make, I'm trying really hard to precisely make here. So weight is a force and mass is a quantity. So I'll line them up carefully. And so you can see the black one there got to the bottom first. Let's try it again. So pretty clearly, the black one got there first. Now we've got to explain why. When things rotate, their mass isn't the most important issue. It's the moment of inertia. The moment of inertia is a combination of the mass and where it's located. So you might think that the heavier of the two would get to the bottom afterwards, but it doesn't. It's the one that's got the mass distributed most around the edge. So here's some homework for you. Find out what the moment of inertia of these two objects is and compare it and see if you can calculate the time it will take for them to get to the bottom. For an added bonus, find out whether their speeds are the same or not. And then in the next movie, I'll address the issue of what their speed is when they get to the bottom of the ramp, which is a classic problem that physicists often get wrong when they're put under pressure. Until next time, see ya.
In our course, I'm going to ask you to make responses to your reading. A response is what you thought of the story, the essay, the novel, anything that we've read, your own thoughts and opinions and connections that you've made with the story. The problem is sometimes when students start doing responses, they limit their responses to only talk about whether they liked it or not and how well they thought it was written. And that really shuts down the conversation and the level we can get to our discussions. We want to go much deeper than that. Let me show you what I'm talking about. So, what did you guys think of the novel we just read?
I loved it. It was great. I hated it. It sucked.
This is an example of how students sometimes can limit their thinking by only talking about their likes or dislikes and not taking it any further than that. This kind of limited thinking can span well beyond just talking about a text. So what did you think of the new restaurant, you guys?
I loved it. It was great.
I hated it. It sucked.
Hey, what did you guys think of the play?
I loved it. It was great.
I hated it. It sucked.
So, what do you guys think of Hawaii?
I love it. It's great.
I hate it. It sucks.
Deeper level thinking can apply to anything in your life. How you discuss a great meal you had, or a movie you saw, or a play, or any experience you've had. We want you to really stretch yourself and learn how to speak and think on a deeper, more critical thinking level. So, what do you guys think of Hawaii?
It's really built upon my understanding and appreciation of the Polynesian culture.
The Polynesians are terribly oppressed. The corporations have taken over all these islands.
Hey, what did you guys think of the play?
Oh, the lighting design was exquisite, evocative of our town.
Oh, the blocking was a complete disaster. So messy. The actors really didn't know what they were doing. I thought it was a disaster.
You should really go see it.
What did you guys think of the new restaurant?
I loved it. The appetizers were so creative. The service was impeccable. Delicious.
My fish was overcooked. The vegetables were raw. I don't think I'll ever come back. The atmosphere just makes me edgy.
Oh, but the melding of the French and the Indonesian cuisine, it was so interesting.
And the waiters didn't even remember our order.
So what did you guys think of the novel we read?
I loved it. The character descriptions were so poetic. I really related to the characters, and the plot twist at the end actually made me cry.
I have to say, I found those characters so unbelievable. I mean, that whole description about Uncle Joe and his, I don't know, childhood memory of Christmas.
But what about the drowning? Couldn't you just get into that? Didn't you feel so sad?
I guess I understood the drowning, but I know water, and I just didn't believe that this author had been anywhere near the water.
See, I bought right into it. I felt like it was real, and I could feel it. I was there with them the whole time. I guess so.
Now it's your turn. You're going to have the chance to make responses of your own. Remember what you saw today, and when you make your responses, really make them thoughtful and interesting and come from you. And next we're going to be learning about different levels of critical thinking and other ways you can make your responses. So, what do you guys think of this video?
I loved it. It was great. I loved it.